Hello everyone, today let's take a look at another conditional probability question, Quantipos number 88, which is definitely on the trickier side. So we have 60% of students at a college who got exposed to the flu at random, and if you are exposed and did get a flu shot, the probability you get the flu is 15%, and if you are exposed and did not get a flu shot, then the probability you get the flu is 80%. So like we do with all conditional probability questions, let's define some events. E is the event you're exposed to the flu is the event you actually get the flu, and shot is the event that you get a shot. And let's have our probability space over here. So first thing we know is that 60% of all students get exposed to the flu. So our event E will occupy 60% probability mass of our total space, and then E complement will necessarily have 40%. So now where should our flu bubble go on the diagram? And the first thing we need to realize is that if you are not exposed to the flu, then you cannot possibly get the flu, right? That's just what's implied by the word exposed. So there's going to be no part of flu that intersects with E complement because you can only get the flu when you are exposed. Okay, so this is going to be our bubble flu right here. Now for the event that you get a flu shot, well, that can intersect with all three of these areas over here. That's just because you can get a flu shot and any of the other events can happen at the same time, right? Okay, so now in part A, it's asking us, what is the probability that a person who got a flu shot will get the flu? So the probability of flu given shot, basically. So they're asking me, given that I got a shot, I'm in this bubble, what's the probability I got the flu? So the blue part divided by the green part. So what other information does it tell us? Well, it says that if you are exposed and you did get a flu shot, the probability you get the flu is 15%. So the probability you get the flu, given you are exposed and you got a shot, is 15%. So what is that saying? Well, it's saying when I restrict my sample space to E intersection shot, the probability I get the flu, so the blue region divided by the salmon region, is going to equal 15%. Okay, so this is where it starts to get a little bit trickier, so I'll just give a brief intuition on the Venn diagram and then I'll actually solve it with the formulas. But basically, we're given no information about the size of this shot circle anywhere in the question, but what we are given is that 60% of students are exposed to the flu at random. And the keyword is at random because we know that you being exposed to the flu is completely independent of whether or not you got a flu shot. So that just tells us that the probability that we are exposed, given that we got a flu shot, is just equal to the overall probability that we get exposed. And what is the probability we get exposed? Well, it's just 60%, right? And all that tells us is that this salmon bubble right here, the probability that we are exposed and we get a flu shot is 60% of the total probability that we get a flu shot. Okay, so now this question becomes a lot easier to understand. What's the probability we get the flu given that we got the flu shot? So we restrict our probability space to this green circle. This is the probability we get a flu shot. And we know that 60% of the time that we're in this shot bubble, right, we're going to get exposed. And of that 60% of the time we're exposed, the salmon region, we're only going to get the flu 15% of the time, this blue region. So the blue part right here occupies 15% of 60% of the entirety of the green circle, which is what we were trying to find. And then this is just equal to 0.09 or 9%, which is our final answer. Okay, so how do we think about this without the Venn diagram? Well, let's just solve this using the law of total probability. So when we reduce our sample space just to the people who got a flu shot, well, we know that it's partitioned into two sets, those who were exposed and those who are not exposed. Okay, so this is just the basic law of total probability applied to this equation up here. The only difference between what we've been doing is now we're conditioning on shot. So everything has to be conditioned on shot. Okay, so now remember how we were talking about the probability of being exposed is independent of shot? Well, that just means that we can rewrite this as just the probability of exposed. And then over here on the right-hand side, we can do the same thing. This is just the probability of E complement. Okay, now we can just solve this, right? We were given this term up here. It's just equal to 0.15. We know the probability of being exposed is equal to 0.6. And then we know the probability you get the flu, given that you're not exposed, is 0%. That's what we were talking about at the beginning. And then, well, this would have been 40%, but it doesn't matter because it's going to get canceled out. And we're left with this again, so you get 0.09. Okay, so now one more way you could have solved this is you could have said, well, the probability of flu given shot is equal to the probability of flu intersection shot divided by the probability of shot. This is just the basic definition of conditional probability. And then you could have used the law of total probability on this top term right here. And then you would have gotten something like this because the probability of flu intersection shot is just equal to that probability in each of our partitions, right? So then this term's 0 because the probability that we get the flu given that we did not get exposed is 0, right? And then I can just use the product rule to break this term down into these two terms over here. And again, I know that shot and exposed are independent, so I know that this is just equal to the probability of shot. Now this is what's given to me. I know this is 0.15, and I know this is 0.6. So when I multiply this times this divided by this, well, these are going to cancel. And again, I'm going to be left with 0.6 times 0.15, which will give me 9% again. And I still think it's most intuitive to look at it in terms of the Venn diagram. Okay, now sadly we still have to do part B. What is the probability that a person who did not get a flu shot will get the flu? So probability of flu given shot complement, let's say. So what's it asking for? When we restrict ourselves to shot complement. So I'll draw a circle around shot, and everything outside of shot is shot complement, obviously. So now what's the probability I get the flu given I'm within this region? So this green part right here. So this is going to be green part divided by orange part, and what other information are we given? Well, now the second piece that it tells us is if you are exposed and did not get a flu shot, the probability you will get the flu is 80%. So probability of flu, given you are exposed and you did not get a flu shot, so I'll say shot complement, let's say, is 80%. So that means when I restrict my sample space to E intersection shot complement, which will look something like this, everything inside of this red shaded region here, well then the probability I get the flu is 80%. So the magnitude of this green region divided by the red is 80%. Well, what else do I know? Well, I know the magnitude of the red region comprises 60% of the orange region. And how do I know that? Well, that's just because the probability that I'm exposed, given that I do not have a flu shot, is just equal to the probability that I'm exposed because these two events are independent. So now just by looking at the Venn diagram, I know how to solve this, right? The magnitude of the green region comprises 80% of the magnitude of the red region, which in turn comprises 60% of the magnitude of the orange region. So what percentage does the green take up of the orange region? Well, it's just going to be 0.6 times 0.8 or 48%. More formally, all we did was use the law of total probability on this to break it down into its two parts, E and E complement. And when we do so, it would look like this, and it would be much the same as part A. Again, we know that these are independent, so this is just equal to the probability of E, which is equal to 0.6. This is what we're given, it's 0.8, and we know that we cannot get the flu if we're not exposed to it, so this is going to be 0. And again, we get 0.8 times 0.6, which is 0.48. So again, ton of different ways to solve this problem, but I always prefer the Venn diagram because it makes a lot more sense to me what's going on, right?